Welcome friends. In the last lecture we had seen how we can obtain the gain margin and phase margin through Bode plot and polar plot on graph paper. In this lecture we will see how we can determine the phase margin and gain margin for a system transfer function analytically, that is by mathematical means. So we shall pick up the transfer function gs equal to k divided by s into 0.2s plus 1 into 0.05s plus 1. So let us start systematically for the analytical treatment of the transfer function. So I am rewriting it for your convenience. We have g of s equal to k divided by s into 1 plus 0.2s into 1 plus 0.05s. So g at j omega can be written as 1 divided by j omega into 1 plus 0.2 into j omega into 1 plus 0.05 into j omega, where k is taken as 1. So we can write g at j omega equal to, if we are going to rationalize the denominator, so we will gradually multiply the numerator and denominator by the complex conjugates. So the terms will become like this: first factor minus j by omega, second factor the complex conjugate 1 minus 0.2 into j omega divided by 1 plus 0.2 omega whole square into 1 minus 0.05 j omega divided by 1 plus 0.05 omega whole square. So we can keep one more bracket outside so that there should not be any ambiguity. So this should be equal to, I am multiplying minus j term to this factor, so we'll get minus 0.2 omega minus j multiplied by 1 minus 0.05 into j omega. This will be divided by omega into 1 plus 0.2 omega whole square, square bracket close, then the next square bracket 1 plus small bracket 0.05 omega whole square, square bracket close. Let us go a little ahead. So g of j omega becomes equal to, if we multiply the terms of both the factors and open the bracket, then the real term and complex term, real term and imaginary term can be separated like this: minus 0.2 omega, first two terms multiplied in each factor, minus 0.05 omega plus minus 1 plus 0.01 omega square into j. This is the numerator and the denominator is as it is, omega into 1 plus 0.2 2 omega whole square into square bracket 1 plus 0.05 omega whole square bracket close. Now if I want to find out the phase crossover frequency, so naturally this is crossing the negative real axis where the imaginary component is 0. So as because g at j omega has been obtained in the complex form of a plus jb, so the imaginary component should be made equal to 0 at the phase crossover frequency omega cp. So we have imaginary part of g at j omega equal to 0. So this means the imaginary part becomes 0. So this is the imaginary part, this becomes 0. So it becomes minus 1 plus 0.01 omega. Now this is phase crossover frequency. Square of this equal to 0. This is very easy. We can find out by oral calculation. Omega Cp is 10 radians per second. This is 10 radians per second. So at the phase crossover frequency we can obtain the gain. So the gain should be mod of g at j omega should be equal to we place the value of omega, so it becomes 0.25 multiplied by 10. The negative sign will go because this is modulus. In the denominator we have omega equals to 10 multiplied by the bracket terms if we into 1.25. So then it becomes, this is equal to, actually this 0.25 and 1.25 will cancel for 5. So this becomes 1 divided by 5 into 5 equal to 1 divided by 25. So naturally this is equal to 0.04. Now as because we got the gain of the system for phase crossover frequency, so this value of gain will help us in getting the gain margin. So what is the value of gain margin in decibels? We can find out gain margin in decibels is minus 20 log base 10 of A. This is again equal to 20 log base 10 of 1 by A. So 25. So this means this should be equal to 20 log base 10 into 25. So this means we have gain margin in logarithmic. This is equal to 20 into 2 because this 5 is 5 square. This is 5 square. So then we have 20 into 2 of log base 10 5. So this is equal to basically 40 into, this is something around 0.7. It means this is 28. So this amount is approximately 28 and this will come in decibels. So from this you can find analytically how the phase crossover frequency can be used to determine the gain margin. So if we proceed further to find the phase margin, we have to obtain the gain crossover frequency first. So to obtain the gain crossover frequency, we understand that the plot or the function for which we can draw the polar plot or Bode plot, they should have a gain of 1. So we can write it in this way: mod of g at j omega is at omega equals to gain crossover frequency should be equal to 1 by definition. So if we look back at the problem, we have, the problem is k divided by s into 1 plus 0.2s into 1 plus 0.05s. So we have taken k equal to 1 and placed s equal to j omega. So directly if I take the magnitude of this, I can obtain it in the form of 1 divided by omega square root of 1 plus 0.2 omega whole square into 1 plus 0.05 omega whole square. Those who are little worried about how to find out the magnitude, they may kindly refer to my erstwhile videos which I have placed for the polar plots, and you can obtain the magnitude very easily by watching those videos. So this is equal to 1. If we take the reciprocal and square both the sides, you will get by taking inverse, that is multiplicative and squaring both the sides, we get so this is very simple. Becomes omega square, then you have 1 plus 0.2 omega whole square, the bracket of this, then 1 plus 0.05 omega whole square, this is again bracket, this is equal to 1. So from there, see, we got lot of omega square terms, so let us make it simple by assuming that s equal to omega square. So in that case we can write simply as x into, so we open the brackets by multiplying the terms and it becomes 1 plus 0.0425 x plus 100 into 10 power minus 6 x square. So this should be equal to 1. But you can see this term is the third term is quite negligible as compared to the first two terms. So the third term can be assumed to be 0. So we make the solution little easy, and without any loss of generosity we can solve the problem with approximate solution. Because we have computers these days, so solving such problem on computer is not a big deal, but when you are solving manually, especially we are writing in the exam, so we need to make such approximations. So it becomes x into 1 plus 0.0425x equals to 1. So if we take the terms on one side, it will become 0.0425 x square plus x minus 1 equal to 0. So now this becomes a quadratic equation which you can solve easily by applying. We have the quadratic form of ax square plus bx plus c, where we can solve for x in terms of minus b plus minus root b square minus 4ac by 2a. So there, if we place the values, we will get x equal to minus 1 plus square root of 1 plus 0.17 divided by 2 into 0.0425. So this is plus minus. So let us understand that this term should be greater than 0. So we take x equal to minus 1, the positive term, square root of 1 plus 0.17 divided by 2 into 0.0425. So here we have this value solved to get x equal to minus 1 plus square root of 1.17 divided by 0.085, and this is approximately equal to 0.961. So here we find that this is nothing but omega square. So this is nothing but omega square. So the value of omega should be equal to square root of this. So this is 0.98. This is the radians per second, and this is naturally the gain crossover frequency, omega Cg. So at the gain crossover frequency we will find the phase margin. So again, if we see the transfer function in the beginning where I have placed s equal to j omega, then we can write very easily g at j omega equal to, so first 1 by s term will contribute to minus 90 degree phase, which is very simple, that was minus j by omega. So then the second term is 1 minus j omega into 0.2, so that will give a phase of minus 10 inverse of 0.2 into 0.98 is the gain crossover frequency. So here the third term is again minus 10 inverse 0.05 into the gain crossover frequency, and this we can solve for minus 90 degree minus 10 inverse of 1.96 minus 10 inverse of 0.049, and thus we can have the angle of G is minus 90 degree minus 63 degree minus 2.8 degree, and which is equal to minus 155.8 degree. So this I have calculated in advance for the sake of saving of time, but you, when you are watching this lecture, you can pause the lecture and do your calculations yourself and verify whether the answer is correct or not. So from here we can find out the phase margin equal to 180 degree that we have discussed in the last lecture. So this phase will always come in the third quadrant, that is minus 155.8 degree. If the phase comes in the third quadrant, this is definitely a stable system because phase margin is going to be positive, and the value of this is 24.2 degree, which is a relatively good answer. In the range of 20 to 40 degrees are relatively good examples of relative stability of the system. So I got the gain margin, which is approximately equal to 28 decibels. So phase margin is positive. Now in this way we can obtain the gain margin and phase margin analytically. So in the situations when you cannot determine the gain margin and phase margin using Bode plot or polar plot, you can go for the analytical treatment, because when we have to find out a transfer function solution which is of a higher order, then drawing Bode plot and polar plot may be little difficult. So this much is for today, and in the coming lecture we shall bring few more parameters of frequency domain analysis. So I always suggest a very simple textbook on control systems written by Professor M. Gopal from IIT Delhi. This book can be referred as textbook, and in addition, if you want to find more problems or examples of control systems, you can refer to these two books also. All these books are available as ebook online. So if you like today's lecture, please like the video and subscribe the channel to stay in connection with me. You can write me through my email ID controlsystemsfaq@gmail.com. Friends, thank you for your patient listening.